Welcome back after the break. It's me again.
And me again.
We hope you had a good break. We're into the home stretch for the day, just 3 talks remaining. Once again, please continue posting on the social wall and the discussion forum. If you have any questions that don't get answered in the Q&A session, post them on the discussion forum and the speakers can engage with you. And then once again, just a reminder, post your questions on the Q&A with Slido and try and do that before the end of the talk so that we can get to it.
All right, well, our first speaker of this session is Professor Shazrene Mohamed. She is a computational stellar astrophysicist. She completed her undergrad studies at Harvard and obtained her PhD in astrophysics from Oxford University. Her talk is on the sunny outlook for computational stellar astrophysics.
Do love a good pun.
Over to you, Shazrene.
Thank you so much. And thank you very much to the organizers for giving me this opportunity to speak to you. Afternoon, everyone. As Bernie Fanneroff explained in his talk, we really are in a golden age for astronomy. And those golden rays from the mega missions like SALT, Meerkat, SK are shining down on many different fields. And I want to convince you that they're shining down also for computational stellar astrophysics. So stellar astrophysics really is a keystone for astronomy. It connects the largest scales. We heard Roy Martins talk about the first stars, the cosmic dawn, and connecting cosmology. And then it connects the smallest scales. Stars are responsible for the heavy elements in our universe and for the molecules that are important for life. So from the largest right down to the smallest scales. We have a rich history and lots of observations. And the way we try to make sense of this history and observations in stellar astrophysics is we experiment, but our subjects are not things that you can put in the lab. And so the way we experiment and interpret what we observe is through simulations. So in computational stellar astrophysics, what we do is we have some equations, some physics that represents our problem, that captures the physics that's important. So for example, for stars, we model them as fluids, and you can see here the fluid equations. There's conservation of mass, conservation of momentum, conservation of energy, and an equation of state. And you set up your problem so that it has some initial conditions, some initial setup, and then you have a solver that solves those equations and evolves those equations in time. And that's how we experiment and test our understanding of the theories of stellar structure and evolution. Now, these solvers, they're different approaches, and you can think of these solvers, they go into a code. So these equations and solvers go into codes, and you can think of them as observers do for instruments. Different instruments can do different things. They have different resolutions, different sensitivities. They work at different wavelengths, and so with codes. And you pick the code that you need for your problem specifically. And on the left here, you can see this is a particle simulation. This is a smooth particle hydrodynamics simulation. And here you represent those fluid elements as particles, and they obey those equations. This is very good for simulating binary stars, where you're interested in conserving angular momentum and for modeling arbitrary geometries. On this side here, you see a kind of grid code where we're interested in modeling and capturing shocks and instabilities very accurately. And so here we use what's called a moving mesh code, where you can actually see that the mesh actually distorts and changes with time, but it's very good at capturing the shocks. And so you need to pick the right tool for the problem at hand. And these are the types of codes that we use in our studies. And then, as astronomers would do, the observers would do, they would take their instruments and put them on telescopes. Well, for us, our telescopes are the supercomputers. And just as in observing, you want the biggest that you can possibly get. We've come a long way from the early supercomputers in the 60s, which could do 1 million floating operations per second. And now we have supercomputers which connect millions of CPUs and GPUs, and they are petaflop type machines. They can do 1,000 trillion calculations per second. So they're really, really powerful. These CPUs talk to each other. They have fast interconnect, sort of like nerves connecting cells. and you can do many, many computations in parallel. And so we put our codes on these supercomputers. And these types of techniques really pervade all of our lives, much more than we probably realize, from big engineering type problems like aerodynamics to modeling how proteins fold and studies of Alzheimer's disease, to very mundane things like the shape of your Pringles chips, or even in the movies. This is a movie from Lord of the Rings, a clip, and you can see the magma that you see there, this flowing magma, is actually modeled with smooth particle hydrodynamics. So you can see those flows there. And if you continue to watch, you can see beautiful, beautiful magma flows. And so if my predictions for the weather report, the sunny outlook, don't turn out so well, it's always good to have a backup plan, and you can go into one of these fields. But what I work on is computational stellar astrophysics. I apply this to stars, and particularly I thought I would focus on binary stars because I wanted to show the interplay between the observations and the theory, and how those two things working together really, really drive our understanding of stellar astrophysics. Itume Leng already gave a very nice introduction to binary stars, so I urge you to go and look at his talk for that. So we usually start with some kind of puzzle, and for the part that I'll talk about today, I'm focusing on a system called Myra, and it consists of a big pulsating red giant star called an asymptotic giant branch star. It undergoes big pulsations which drive a dense stellar wind, and it has a companion, which we think is a white dwarf, at about 100 AU away. And what was surprising about this system was that despite the fact that the orbital period is about 1,000 years, this white dwarf seems to be having a very strong effect on the outflow, on this dense wind from the giant star. And this was unexpected. We don't expect such wide binaries to have such a strong interaction. And that was just one individual star. But then when we look at populations of these things, and you can see this on the right, when we look at whole populations of stars that have gone through this type of binary interaction, you see a very disturbing trend. This is a plot of the orbital eccentricity versus the orbital period, so how eccentric the orbit is versus how long the orbit is. And you can see that in the grayscale, that's what the models predict, our best models of binary interaction theory. And the crosses are actually what is observed. And so they really, really don't agree at all. And so we have some fundamental problems with our understanding. And so what we proposed was that the reason for this was that we don't, when we model these binary interactions, we don't take into account the physics of how these giants lose their mass, and that the winds from these giants are actually much slower than we previously used in the models. So we want to test this. And you can see this is a simulation here of one of these binaries. This is looking at the gas density. So the brighter it is, the denser it is. You can see the pulsating giant star losing its mass, and it has a companion, a point source white dwarf, which is stripping off some of that mass and really focusing that mass through an accretion disk and then capturing some of that mass. Part of the material is lost in these spiral arms that you see forming here, but a lot of the material is actually captured by the companion. And so you can have a very strong interaction even if you have a wide orbit. And we call this mode wind-Rho-Slope overflow, where the wind is really being channeled and focused onto the companion star. This is another plot of the gas density. On the left, you see a slice in the binary orbital plane, and you see that the companion, that material that was coming out as a spiral forms this really 3D spiral structure, kind of like a snail's shell. And if you look on the right, you can see what it looks like if you take a cut perpendicular to that. And I remember as a graduate student showing this image at a conference, and a very senior scientist standing up and saying, "Your pictures are very nice, but look, you're plotting on log scale, and we'll never be able to observe this." Well, have we ever? We decided to propose with ALMA, and Moses already talked a little bit about ALMA and CO observations with ALMA. But we wanted to study on the left, you can see this detached shell around a giant star called R Sculptoris. So we knew about the shell and we wanted to study it. And when we looked at it with ALMA, what we found was a spiral inside that detached shell. Well, having modeled spirals, for my PhD and ad infinitum, I was thrilled because I knew exactly what this meant. It meant that R Sculptoris was not a single star, as we had originally thought, but it was actually a binary, and it had a hidden companion. And then the interplay between the models and the theory, we were able to actually constrain what that companion is. So we think it's a 0.2 solar mass star at about 60 AU away. We also looked at MIRA to really test this wind-Roche-Lobe overflow, this mass transfer theory. And you can see the cross on the left is the white dwarf, and on the right is the giant star. On the left figure, you have the CO gas, so tracing the densest gas. And on the right, you're looking again at the densest structures, but this time in the dust. And you can see that many of the structures that we see are very similar. So you have cavities, as you do in the ALMA observations, but we also have these dense arms coming out, flowing towards the bottom, as well as arms going towards the top. So I think that we are on a good track to really trying to understand how these systems interact with each other. And now we're doing full parameter studies to really get a good prescription that we can put back into the population synthesis models so that we can really try and reproduce those populations better. We're also interested in what happens on even smaller scales. So these giants, as I said, they pulsate and they produce shock waves. And if you have a planet nearby, it can interact with those shock waves and enhance them in places and weaken them in places. And this can result in multiple different spiral structures forming, depending on the resonance between the pulsation period and the orbital period of the planet. This is work that was done by my student, Elias Saidi. He's currently a postdoc, and we're preparing this for publication. And again, you could ask, well, will we be able to observe this? Well, this is the paper that just came out in Science, and you can see these are structures around these giant stars. They're on slightly larger scales, so hundreds of AU, whereas here we're looking now simulations at tens of AU. But I think we're on the right track to really being able to test these theories. And if we can find these structures, then we can actually find planets around these really bright giant stars. So this is somewhere where the models are making some predictions, and we'll have to see how the observations come out. We're really interested in what happens to the gas that leaves the giant. What happens to it when it lands on the companion? Well, we know that if the companion is a white dwarf, that gas can form a hydrogen layer around the white dwarf, and it can get hot enough to actually ignite. And when that happens, you get a thermonuclear runaway, a big explosion, like a thermonuclear bomb, on the surface of the white dwarf. And we call these explosions novae. And it turns out that if you assume a spherical nova explosion, you don't always get a spherical shell that's formed from the explosion. It depends really on that binary mass transfer phase before the explosion, how the mass is distributed. So this is a 3D simulation, again, looking at gas density. And here we're looking on the left, pole on, so looking above the orbital plane, looking down on it, and we see a spherical explosion going off on the white dwarf surface. It interacts with the material that was pre-existing. You get a spherical shockwave moving out and these dense instabilities, which you can see. However, these are 3D models, and we can look at a different angle. And if you look at a high inclination angle, you'll see that that dense material that was pre-existing really constrains the fast-moving explosive material, the ejector. And you end up with a waste and these bipolar outflows where the material can flow freely in the polar directions and really be constrained in the orbital plane. And so you get very, very different views depending on what angle you look at these systems. Now, there are systems that have been observed which are called recurrent novae. So they do this binary mass transfer, explode, binary mass transfer, explode several times within a human timescale, a human lifetime. And at the top, you can see our simulations. This is a single simulation. On the left, you're looking down at the orbital plane, and you can see the nested structures. So it looks like nested explosions. And on the right, you can see the nested bipolar shapes when you look at it edge on, so looking at high inclination angle. And of course, we want to compare this again with the observations. And these at the bottom, you can see observations from the Hubble Space Telescope of two systems. This is TPIX. And it turns out when you look at the kinematics of TPIX, you look at the kinematics of the gas, you are indeed actually looking at a bipolar structure, pole on, so looking down at the orbital plane. Whereas for Iris of Yuki, which is another recurrent system, we're actually looking at it at a higher inclination angle, and you can start to see that bipolar structure. It doesn't look spherical. So we're hoping to study these things, not just individual systems, but really big whole populations. And I think the things that are already online, like LIGO, and the future missions that are coming, make the future blindingly bright. For the black holes and neutron stars, this mass transfer really will determine what mass of a black hole you form, whether you form a black hole at all or you form a neutron star. So the spotlight again is on the stellar astrophysics and really understanding the theory of mass transfer. For the Rubin Observatory, once they stop looking at broccoli and start looking at the sky, we'll get beautiful populations of transients, of exploding stars that will really again test our theory. With JWST, we'll be looking at the cold gas in the infrared, and so we'll really be able to probe the planets, to probe these dusty outflows from the giants. And we heard from Phil Diamond about the SKA and how computing is really going to be a huge component of this. And that's true also for the LSST. We're going to need exascale type computers. So that's 10 to the 18 floating point operations per second. So really, really powerful supercomputers are going to be needed. And that's going to mean that we can run simulations with all sorts of complex physics. Our wish list will really be unlimited. So it's really, really an exciting time. And I think the observations and the theory really are going to play quite well together. Of course, it's not all sunshine and rainbows. There are issues, and this was already discussed earlier, particularly on the computational side and in theory, we need to transform astronomy. I often say, I'll know that things are okay once I can look at a conference picture and really have to hunt for myself. But we're working on this. We have a group. We've been going for about 1 year, really working on addressing the challenges and issues facing women and Black women in astronomy, women of color. And we'd like to invite you to our first speaker series. You can go to this URL here that you can see to find out more. The other thing that keeps me up at night is our impact on the environment and on our planet, and particularly supercomputing. So I grew up with Captain Planet, this cartoon, and I thought of myself as an eco-warrior. And the bad guys were the mutants who were, and these big corporations who were polluting. And then there was this article recently in Nature Astronomy where they did look at the impact of astronomy on our planet. And it turns out that supercomputing contributes hugely. So we really have to change and address the way we do our supercomputing. I've been putting off looking at GPUs, but maybe this is really worth investing the time to use GPUs where we can. Popular languages like Python are also really not good for the environment, so we should shift away from those, focus on using really efficient algorithms and really good equipment. And as Phil Diamond said, really looking for green, sustainable ways to power our supercomputers. So barring those challenges, my take-home message, whatever home means these days, we have other challenges like COVID, and this cartoon says, do I work at home or do I live at work? It was bad before the pandemic, but now I think it's particularly difficult to know the answer to that. But given what's coming with the observations and the computing, I think the future is really, really bright for computational stellar astrophysics. And we can discuss this and see whether my prediction is true. We'll share what happens at the GA in 2024. Thanks very much.
Thank you, Shazrene. Thank you for the talk and for some wonderful messages there at the end there.
We have a few questions on Slido. We'll start with the first one that came through from Natalie Jones. She says, thank you so much for your presentation. What do you love most about being a theorist, and what is your message to encourage learners, especially females, into astronomy?
I think It makes you feel very powerful. I say a small god with a small g, because I make stars. I simulate them, and I feel very, very creative and powerful in doing that. It's challenging. It's difficult. I think I wouldn't enjoy it if it wasn't challenging and difficult. When you have a problem and you really struggle with it, when you have that moment where it comes right, your eureka moment, it's the most wonderful feeling. For example, when I had run those simulations and then seeing an observation that looks like my simulation, I cannot even begin to explain how that feels.
It must be absolutely
for-
amazing.
Yeah, it was. I always say if I could do somersaults, I would have done somersaults, but I can't do somersaults. So, but it was really, really an amazing time. I think for young people, really follow your passions. You can do it. I think there's a lot of this idea that astronomy is for geniuses, or astronomy you really this is not the case at all. Everybody can do astronomy. Astronomy is for everyone. Someone said, Huzo said, the sky is for everyone. And I think that's really true. We've been doing it. It's part of our heritage. It's part of our DNA. It's part of us, and anybody can do it. So if this is what you want to do, definitely go for it.
Thank you, Shazrene. We've got one other question here on Slido. Sarah White asking, is it possible to model how the spins of a pulsating star and a companion evolve over time? Is that something you work on?
Yes, it is. We are interested in this. It turns out that when you transfer mass, you also transfer angular momentum. And you can actually keep track of how that mass and angular momentum is transferred to a companion. So you can actually keep track, yes, of how the spins change. So if you have a neutron star, I don't know, I think Sarah likes maybe neutron stars, pulsars. If you have a neutron star, you can actually see how transferring angular momentum can actually spin up a neutron star. And we think that this is how these neutron stars actually can maintain their spin. It's through this mass transfer with a binary companion.
Great. Thank you, Shazrene. Thanks once again for joining us and for your contribution.